Hello and welcome all. My name is George Philip. At the end of this video, you will be able to understand fin efficiency and its importance in design and selection of fins. The question is, what is a fin? A fin is nothing but an extended surface which is used to dissipate heat and hence enhance the cooling. By definition, eta fin or fin efficiency is defined as the ratio of actual heat transfer to the maximum heat transfer that is possible. Now I'll look at it in detail. Actual heat transfer. Now let us consider case A. I have denoted the actual heat transfer as QA, where A stands for the case A. I have taken a fin. Now the fin is at x equal to 0, the temperature of the fin is T0. At x equal to L, my temperature of the fin is TL. Now this fin is made of a material which has a finite value of K, the thermal conductivity of the material. Now, as K varies, the values of TL for the same T0 will also keep on varying. I have plotted the variation for different materials. Now, if you look at this carefully, if I change my material, the temperature at the end, TL, will keep on changing for the same value of T0. Now, I have arranged these materials in the order of decreasing K. Now, as K decreases, it is seen that the value of T0 minus TL keeps on increasing, or in other words, the temperature gradient across the fin over a length L keeps on increasing as my value of K decreases. Vice versa, if my value of K increases, the temperature gradient across the fin is much lesser. Now Q actual is the heat transfer through this case where I am having a fin of length L made of a material with finite value of K. I have taken a case where the tip of the fin is insulated, that is, there is no heat transfer from the tip of the fin, or in other words, the shaded area does not there is no convection of heat from the shaded area to the surroundings. Now the surroundings have a temperature T infinity and the convective heat transfer coefficient is H. The perimeter of this fin is P equal to 2 times B plus T, where B is nothing but the breadth of the fin and T is the height of the fin. Now what is the maximum possible heat transfer, which I have denoted as QB, as sketched in case B. Now when I say maximum heat transfer, when I say Qmax or Qmax possible, I am referring to the fact that since there is a temperature variation, the amount of heat transfer is reduced. So if I keep the entire fin surface area at the same temperature, I will achieve something known as Qmax possible. Now for that to happen, for the maximum possible heat transfer, this entire area has to be at the same temperature. Now which means if the entire area has to be at the same temperature, T0 and TL should be equal, that means K should be infinity. So I consider a hypothetical case. I am using the term hypothetical because no material has an infinite thermal conductivity. I have taken a hypothetical case where the thermal conductivity of the material is infinite, which means that the temperature at the root as well as the tip, they are equal and they are equal to T0. That is, at x equal to 0 and x equal to L, the temperature is T0. Now I have taken the same assumption here, that is the tip of the fin does not transfer heat, or in other words, the fin tip is insulated. Now as per definition, Q actual upon Qmax possible is nothing but the ratio of QA by QB. Now for an insulated tip fin, I know that QA is equal to square root of HPKA T0 minus T infinity tan HML, where M is equal to square root of HP by Ka. I just repeat, M is equal to square root of HP by Ka. Now H is the convective heat transfer coefficient, P is the perimeter of the fin, K is the thermal conductivity of the material of the fin, and A is the area of cross section, that is the area which I have shaded here, or in other words, A is equal to B into T, the breadth into height of the fin. Now QB is nothing but the heat transfer from this hypothetical fin exposed where the entire area is at temperature T0 and exposed to T infinity. That can be calculated using your Newton's law of cooling, which states that the total heat transfer from case B will be equal to H into area of the fin multiplied by Ts minus T infinity, where Ts is nothing but the surface temperature. Now substituting the values, I have QB is equal to H into area of the fin, AS. The surface area of the fin is nothing but the total area exposed to the fluid at T infinity having a conductive heat transfer coefficient H. That is nothing but the perimeter times the length of the fin, that is P into L, times temperature of the surface, that is nothing but T0. The entire surface of the fin is exposed to temperature T0. So that is T0 minus T infinity. Now let this be equation number 1. Substituting these two values in equation 1, I'll get eta fin is equal to QA by QB, that is equal to square root of HPKA T0 minus T infinity times tan HML hyperbolic tan function divided by QB, that is H into T into L times T0 minus T infinity. Simplifying this, I can write it as tan HML upon ML, where your M is nothing but square root of HP by KA. Now this is the expression for the fin efficiency if my fin tip is insulated and the fin is of a finite length. Now here I have considered a fin which has its tip insulated. Instead of using an insulated tip, if I give the allowance that the tip is also capable of transferring heat, then in that case, if I use a fin with the tip being non-insulated, then I have eta fin is equal to tan HMLC upon MLC, where LC is the corrected length which allows for this area to be also taken into account. Now for a rectangular fin which I have sketched in this case, my LC or my corrected length LC is equal to L plus T by 2. Now instead of using a fin of rectangular cross section, if I had taken a pin fin or a fin which has a circular cross section, then in that case my corrected length would have been L plus D by 4, where D is the diameter of the cross section of the fin. Now if you look at both the expressions for eta fin, it is very clear that eta fin is inversely proportional to the value of M, where M is nothing but square root of HP by K. Or in other words, I can write eta fin, substituting the value of M, I'll get that eta fin is proportional to square root of K. Now higher the value of thermal conductivity, higher will be the efficiency of the fin, and hence the fin will approximate more towards the case where the entire fin is at the same temperature or the root temperature, the base temperature T0. I hope I have clearly defined what is the fin efficiency, and I have given you an expression for the fin efficiency for two cases, for fin with an insulated tip and a normal fin without an insulated tip. In both cases the expressions are similar, the only thing being L is replaced by LC in the case of an uninsulated tip. Now if you look at it carefully, eta fin is a parameter which shows you the amount of heat transfer, which gives you an expression for how much is the heat transfer compared to the case where the entire area was at the same temperature. Now obviously higher the value of eta fin, more is the heat getting more is the heat getting transferred, or more is the efficiency of the fin, which means that what are we using fins for? Fins are nothing but extended surfaces which are used to dissipate heat. So higher the value of eta fin, more heat is getting dissipated, and hence my purpose is getting served. So that is why eta fin is one of the fundamental parameters when taken into account when we discuss about fin design and selection. I hope my video is clear to all of you. Thank you. Please like and subscribe if you like the video.